Chemical reactions are when we observe a chemical change, a color change, the formation of a gas, or the formation of a precipitate. Now there are 5 basic types of reactions: synthesis, decomposition, combustion, single replacement, and double replacement. What I would like you to note as we cover each type is the pattern that is present. And that pattern is what allows us to ultimately predict products. The first reaction is synthesis reactions, otherwise known as combination reactions. Burning of magnesium ribbon is an example of this synthesis or combination reaction. Basically what's going on is we see 2 or more substances forming a single product. That is one of the ways that we recognize it. We have one thing on the product side. So we see a couple of things and we get one thing. Examples would include nitrogen reacting with hydrogen, producing ammonia, and a propane reacting with bromine to form a bromide carbohydrocarbon. Notice that every single time I have a single compound or a single substance in the products, just like in our pattern. This is the way you will always recognize a synthesis reaction. The other thing I would like you to note is that when I see 2 elements being formed, the compound is the compound of those 2 elements every single time. Sodium and chlorine will form sodium chloride, etc. Decomposition reactions are literally the opposite, decomposing. We're breaking something down. So, for example, water is formed from hydrogen and oxygen, so I can actually decompose water to produce those gases. Decomposition always has a single reactant, and I'm getting multiple products. So I have a single reactant, I get multiple products. Notice that this is literally the reverse of a synthesis reaction. So in all of these examples, I have a single reactant, I get multiple products. Notice when I have a 2-element or a binary compound, I'm getting those 2 elements being separated. Combustion reactions are what we typically talk about when we say something is burning. We say it's combusting. In chemistry, combustion reactions are actually a little bit more specific. They're usually fast, there's almost always a flame, but it involves a hydrocarbon reacting with oxygen. And remember that a hydrocarbon is basically a carbon-hydrogen compound. So propane, ethane, butane, what we burn in our Bunsen burners, etc. The products are also specific. And I've added a little word here. Complete combustion will always produce carbon dioxide and water. So combustion reactions are very easy to recognize. I get carbon dioxide and water. I have oxygen as one of my reactants. I have some kind of carbon-hydrogen compound. Very simple, very straightforward. Replacement reactions, there's actually a lot more chemistry going on than what we've been dealing with synthesis or decomposition or combination. There's more going on behind the scenes. In these, we're usually dealing with a single element replacing another element in a compound, or we're talking about the exchange of ions. So in a single replacement reaction, we have an element replacing another element in a compound. So in the example here, there's copper wire that's been put in silver nitrate. Notice that the copper wire is nice and coppery, and it's a nice clear solution. And over time, we see the buildup of this solid silvery compound on the wire, and the solution is turning blue. What you will notice is that we're actually looking at a transfer of electrons. So, the silver was originally in solution, and it became solid silver. So notice it went from a plus to no charge. That means it gained electrons. Conversely, notice that the copper had no charge, and then it became charged, meaning it lost electrons. So when we talk single replacement reactions, what we're actually talking about is this exchange of electrons. But there's also 2 kinds of replacement reactions. We have what's known as cation exchange and anion exchange. Notice in cation exchange, it's actually literally where we are replacing an element's replacing the cation in the compound, and so we have a new compound with that cation. In anion exchange, we have an element replacing the anion in the compound, and we get a new compound. This does require that you recognize anions and cations, and you have to remember one phrase: like replaces like. So metals are often cations, they will replace the cation in the compound. Nonmetals are my anions, that means a nonmetal is going to replace a nonmetal in the compound. And there's one other thing to remember: not every metal can replace every other metal, and not every nonmetal can replace a nonmetal. It actually depends on how reactive or active those elements are. So as you can see in this diagram, lithium is the most reactive, gold is the least reactive. You know that from just living day to day because we wear gold jewelry and it does not develop a patina. It does not develop and turn a color. Silver will react, and that's why silver has to be polished. We have to get rid of that dull gray silver oxide that is formed. So what you can see here is that there are different reactivities in the metals, and it kind of goes along to some extent with their position in the periodic table and to some extent the size of the atom. The smaller the atom, okay, versus the bigger the atoms. So we see a little bit of that periodicity playing a role in the activity of those elements. Now the halogens, notice that we have fluorine, chlorine, bromine, iodine, etc. And that the least reactive is at the bottom of the column, the most reactive is at the top of the column. Now, I didn't catch that when I did this, but fluorine should actually be above chlorine. Fluorine is the most reactive halogen. It will always replace all the other halogens. So what's required for a reaction to actually occur, for example, copper can replace silver in a compound, but silver will never replace copper in a compound. So, examples. We can see that copper is the solid single element, silver nitrate. We see copper literally replacing the silver, okay, and the silver becomes by itself. Conversely, we see something similar in the anion, but it's again the anion replacing the other anion, kicking it out of the compound, so we get a new element, new compound. So again, as long as you recognize like replaces like, it's pretty obvious what's going to go where. In double replacement reactions, it actually looks like things are exchanging or trading places. And that switch produces new compounds with new properties, etc. So again, like replaces like. So my cations literally exchange. The C ends up with the B, the A ends up with the AD. Now, there are three types: precipitation, neutralization, and gas forming. In a precipitation reaction, we get a solid in the product. In neutralization reactions, we always form water. And just as the name reads, in a gas forming reaction, we form a gas. So in precipitate reactions, we see two solutions that mix, forming an insoluble compound, precipitate. Notice that in every one of these reactions, the way I recognize it is because I know a solid is formed. And we know a solid is formed because of the little s. Again, you see that the cations exchange. So we see the Ag and the K swapping places. The Ag is with Cl, the K is with the NO3. And similarly, the Pb replaced the K. Now the Pb is with the I, and the K is with the NO3. And that's all precipitate reactions are. So remember, precipitate is one of the ways we recognize a chemical reaction, and this is what's happening to produce it. Now, neutralization reactions are not nearly as obvious as all of our other reactions because we're just forming water. So we have an acid. Remember, acids have hydrogen as the cation, and the most common bases we're going to be dealing with have OH here in the anions. So notice when these swap, when the H and the Na switch places, that H and the Na swap because those are both my cations, okay, I would basically form HOH, otherwise known as water. So in these reactions, what we're actually looking at is we see what's known as a change in pH. And pH is how we measure how acidic or basic something is. Just know if I see water as one of the products with a salt from a double replacement reaction. We're not talking water formed from a combustion reaction where one of my reactants is oxygen. Okay, so this isn't a combustion reaction. But pay attention to what's going on. But if water is one of your products, then it's neutralization. We've actually taken an acid and a base, we've neutralized them, and we just have water. The last one is gas forming. Now, in gas forming reactions, as it says, a gas is produced. Now, what's interesting is sometimes the gas is not the expected product. So here, notice that the calcium and the hydrogen will switch places. So the calcium ends up with the chlorine as we expect. The H ends up with the CO3. We should be forming H2CO3, but H2CO3 actually doesn't form. Instead, that decomposes or breaks down into CO2 and H2O. This is what we observe when we see vinegar and baking soda. Any carbonate or bicarbonate compound that combines with an acid, okay, again, hydrogen and the cation, will always form CO2 gas. That's why this is considered a gas-forming compound. So one more time, notice that we have these very predictable patterns, the exchange of cations in double replacement, a similar displacement in single replacement where like is replacing like, the formation of CO2 and H2O with oxygen as a reactant, a single reactant forming multiple products, and single reactants forming a single product in synthesis. So because of those patterns, as long as you know that pattern, you can always predict the product. Single elements, I get a single product. One reactant, it's going to break into its elements. Like replaces like, and I get the exchange or the transfer or trading places of cations.